This is lecture 4 from chapter 13, and in this section we're going to talk about things like nuclear fission. These are applications of radioactivity. So these are things that we can do to harness the breakdown of those unstable nuclei of those radioactive elements and use them to our own benefit. So the first thing we are going to talk about is nuclear fission. And as you can see here, it occurs when something, usually a neutron, can be other particles, but it's usually a neutron because it has enough mass to do this, unbalances the nuclear forces in the nucleus and the nucleus splits. So as you can see here, we've got a large nucleus of an atom, let's say something like uranium, and a neutron comes in and collides with it. When it collides, it deforms the nucleus because the collision has enough energy to do that. And that deformation, that change in shape, is enough to split the nucleus into two pieces. Now in this picture, it looks like it's equal. It doesn't have to be an equal split. That neutron could split it into two unequal nuclei. But the point is that fission means to divide or to split. And so we're going to get two new nuclei, and generally you're going to get some neutrons coming off of this fission, this split. And so the greater the force that you get, the more you're going to get of these neutrons coming off. So that's what nuclear fission is. Nuclear fission is just something unbalancing the nuclear forces between those protons and the nucleus splitting. When that happens, you not only get two new nuclei and some neutrons, but you also get some energy. So let's look specifically at uranium fission because this is the one that we harness right now. Because it releases a huge amount of energy. So one uranium nucleus of 235, so remember this is an isotope, so this is uranium-235. One individual atom of uranium-235 has 7 million times the energy of a TNT molecule. So remember TNT, that's like dynamite. And so if we have fission occur in one uranium-235 molecule, that's going to give us 7 million times the energy that you get from a TNT molecule. So you can imagine this is a lot of energy. And so you can see down here, we've got one neutron coming in. It hits our uranium-235, so you can see we've got our 92 protons, our 143 neutrons. It hits that nucleus, and we're going to get two nuclei. Like I said, they're not necessarily going to be even, and in this one, we're going to get two. We're going to get krypton and barium. So we get our uneven division, and we're going to release, if you count them up, 3 neutrons at the end of the fission of uranium-235. So we get 2 new elements, and we get 3 neutrons at the end of the reaction, as well as that huge burst of energy coming out of this reaction. Okay? So how do we harness this? Well, the thing is with something like uranium-235, because you have multiple neutrons being released, you get a chain reaction. Because each of the released neutrons can now run into a new uranium-235 atom if you have them around. So here we have our initial guy. So you get hit once with a neutron, it splits, and you have your neutrons coming off. Now here in this picture they're showing more off of the first one, not exactly sure why, because it's usually just the 3, but you've got 3 going off and hitting 3 more uranium-235s. Each of those has the potential of hitting new uranium-235s. This one doesn't hit anybody, but this one is going to hit 2. This one is going to hit 3. All right, and you can see that this is just going to expand farther and farther out. And so you get more and more of the reaction going out from just that one initial hit at the beginning. And so what will happen in a very short time, you will get lots of these neutrons flying around, hitting uranium-235 atoms, releasing that amount of energy, and you'll get a huge amount of energy released in your reaction chamber. So let's think about this. We know we have deposits of uranium sitting around the world, so why aren't uranium deposits exploding? Because we know that they're decaying, we know that they're getting hit by neutrons and so forth, and their nuclei are breaking down. So why isn't uranium just exploding all over the planet? Well, there are a couple of reasons, and the big one is that most uranium is actually not uranium-235, the one that is highly fissionable, meaning that it really splits easily. So most uranium is uranium-238. Only a fraction of a percent is uranium-235. So less than 1%, 0.7% is uranium-235. And they're mixed together. So uranium-235 and uranium-238 are mixed together in these deposits. So if this is a section of uranium, the 235 would be all spaced out through this rock. So if a uranium-235 atom does split, uranium-238 doesn't fission very easily. In fact, it tends instead of splitting in a fission reaction, it just tends to absorb neutrons. It will be radioactive and it will undergo radioactive decay. However, if there is a 235 nucleus that undergoes fission and splits, those neutrons will just be absorbed by uranium-238 and it'll stop the chain reaction, right? So imagine we have our little 235 here, and let me change the color. So that's 235. These all around it would be 238. So no matter what, if this 235 goes off in any direction, because the percentage is so small, if that (235) would to split, its neutrons, if it goes into any direction, it's going to end up hitting one of these 238s. And so it's going to end up just stopping the reaction and not going any farther. The other thing is even if you have fairly high concentrations of uranium-235, they're usually in very tiny chunks. And so that's what this picture over here is. So uranium-235, like I said, very small concentration. So even if you have a small chunk of uranium-235, you're not going to get enough of the reaction happening to get it to get enough heat to explode. Because what happens is you get the neutron coming in, it hits the uranium-235 like you see here. It starts the chain reaction. The problem is because of the surface area, the large surface area on this piece, the neutrons make it to the surface and escape before they're able to hit too many of the other uranium atoms inside of the chunk, and they can't build up enough of a chain reaction to create the energy, to create the heat to generate an explosion. right? And so here you need something larger like this chunk down here in order to get that chain reaction where you get the neutron coming in and hitting and triggering the chain reaction where the neutrons can't escape and build up the reaction. And the thing is that we don't have, in nature at least, chunks of uranium-235 that are this big that allow the reaction to build up and explode. So this brings us to the idea, you may have heard of critical mass in, movies and so forth, talking about nuclear explosions. So what critical mass is the mass of uranium-235 or any radioactive element that's needed to create an explosion. And so the critical mass is kind of two parts. One, you need the actual literal mass of the element that can undergo fission to create the explosion. But it also needs to be in the right shape. And so let's say you need a kilogram of mass of uranium in order to create a critical mass, but it makes a big difference on whether that uranium is in a single ball or if that uranium is a kilogram of little uranium-235 chunks. Because the only one of these that would be able to undergo critical mass would be this guy right here, because it needs to be in that solid chunk in order to build up the chain reaction without losing the neutrons on the outside. This guy right here, the chunks, would actually lose the neutrons too fast in order to build up the heat and energy, like we were just talking about previous slide, to create that critical mass to create the explosion that you'd be looking for as far as this radioactive element. To give you an idea of how long it takes to get radioactive elements to create a critical mass, it took 2 years to extract enough uranium-235 to achieve the critical mass for the Hiroshima bomb. So this tells you it takes a large amount of these radioactive elements in order to create a critical mass, at least for an explosion. Now, most people are familiar with radioactive elements like uranium for explosions. But what we most commonly use them for today is actually for energy. So we use them in what we call nuclear fission reactors. It's using uranium-235 fission, what we've just been seeing, where the nucleus splits, releases that energy, and then the neutrons. So to give you an idea of how useful this is, 1 kilogram of uranium in a reactor makes more energy than 30 freight cars of coal. If you've ever seen the big freight cars on a train, you need 30 of those to make the same amount of energy as a kilogram of uranium. Now, I wouldn't recommend you hold a kilogram of uranium, but you could actually hold a kilogram of uranium with no problem whatsoever. So, huge difference here. Now, in a nuclear fission reactor, there are some major components. One, you need the nuclear fuel. So this is actually combined fuel. It's mostly still uranium-238, and there's 2 reasons for that. One, expense, because we actually need to enrich the fuel to make that percentage of uranium-235 high enough, because we need 3% uranium-235, and it's, again, less than 1% naturally. But the other reason is we're going to use uranium-235 to keep the reaction under control, because it's going to be able to absorb some of those neutrons and keep it under control. We're going to actually have control rods to absorb neutrons to slow the reaction when we need to, because we don't want it to get out of control and turn into a bomb. And we're going to use water to transfer heat from the reactor to the turbine. And so in our next lecture, we're going to pick up, I'm going to walk you through a nuclear fission reactor and see how it works. And we'll also take a look at some of the alternatives of using nuclear fission reactors, because uranium-235 isn't our only option.